So this is what we were talking about when we left off on Tuesday, talking about central angles and radian measure and arc lengths and the relationship between those, and just what the meaning of measuring an angle is. Like, how do you describe what it is that you're doing? You can talk about like, oh, well, it's how open the two rays are from one another, the two halves to the angle, how far apart they are. But when we talk about an angle measure, we're not talking about generally how many like inches or feet or whatever there are between the two rays. It's the degree of openness, or the proportion relative to what it could be, or in other words, it kind of has to be relative to something. And that's why we use the word degree in a variety of ways, just in common speech also. The degree to which, somebody blah, blah, blah. It's all relative to something else. And so we can talk about relative to like a square corner, relative to a circle, but we've got to fix some sort of number to represent a whole, and then talk about a portion of that to measure degrees. So whether we're talking about degrees, like the unit we call degrees, or if we're using radians, they're all relative measures. And radians are the relative measures, again, that are based on the length of a radius of a circle. So the idea is, and just the term central angle, and I don't know if I use that too many times on Tuesday or not, but the word central angle indicates an angle that's kind of situated in a circle with its vertex at the center. And we use this setup just so we have a standard way to think about the setup of angles, where we have what's called the initial ray along the positive x-axis, and then we think of it either rotating or being fixed at a position that would be moved counterclockwise from there. So the direction that we go through the quadrants in 1, 2, 3, 4, that order is the order through which this, what's called the terminal ray, is thought to move to get to this position from this initial position along the positive x-axis, if we're measuring what's called a positive angle. We can talk about negatively measured angles also, like go down a little bit instead of going up and around to get back to that same position. But in any case, if I have a circle with a radius of r could be 1, 2, 3, 17.8, anything you want, although it's going to be greater than 0, then we can talk about an angle in central, like a central angle for that circle of any size. This one I called the size of the angle theta. We could measure it in degrees, we could measure it in radians, we could measure it in gradians, we could make up our own unit of measure. But talking about radians, the relationship that we have in this circle is that whatever this radius length is, 1 radian is an angle that would be just the right size so that the arc that extends between the initial and the terminal rays, that arc length there is 1 radius length. So in this circle, it would be about here or so, where this red line is about the same length as the radius. Someplace in the middle of the first quadrant, we'd have 1 radius length around the edge of the circle. And a second radius length would be maybe pretty close to where I have my terminal ray, but a little bit less than that possibly, because I know that all the way around the circumference of a circle, if I were to go all the way around, because of geometry facts you learned before, not because you proved it in geometry classes, but the circumference of a circle is 2 pi times the size of the radius, 2 pi r, or pi times diameter. That takes you all the way around. And in terms of that means that to get halfway around, that would be 1 pi radians, or 3.14 approximately, radius lengths around the circumference to get to here, this negative x-axis position. And so if that's a little bit more than 3, then you can maybe see, all right, well, you can kind of picture where 1 and 2 must lay out. So this angle here is somewhere between 2 and 3 radians in size, because the arc it subtends is probably more than 2 but less than 3 radius lengths long if we're measuring in length units. You can also talk about arcs having measures in radians also, but you'd have to know what size circle they came from. If I just say, oh, I've got an arc that's 3 radians long, well, you would know that it is almost half of a circle's worth of arc. It's almost a semicircular arc, but that doesn't really tell you how big the arc is, but just what shape it is. Same with angles, though. So in that sense, arcs and angles, you can talk about both of them in terms of their size relative to something else, like an arc relative to what portion it is of a circle, as opposed to just how many inches long it is, and an arc, what portion of a circle or of a square corner of whatever relative whole that you want to talk about. So if I have in general this diagram here, I have a circle with radius r and a central angle, and I call its measure theta, that symbol's theta. If I want to talk about how big this arc is in length units, I can do that because without doing a whole bunch of computations, if this radius was 1 unit long, then I know that this would be 3.14 inches all the way over to here, or, well, whatever portion this is, I can talk about, well, however many radius lengths I've got. If the radius was 1, theta would be the same as the number of inches, because theta radius lengths, theta 1s would just be theta. But if I want to talk about this arc length in general, if the angle's theta, then I've got theta radius lengths to get from the positive x-axis up to that point where the terminal ray crosses the circle again. So theta radius lengths, if the radius is r units long, would just be a length of theta r's, theta times r. So the formula that you'll generally see, and I'm going to write it because it takes a while to type a theta, is that the arc length is just theta times r. So the arc as a length, as opposed to an angle measure that forms the arc, like what portion of a circle that arc is theta, an angle measured in radians, times our radius length. Just measured in whatever length units you want. This comes out in the same length units. If I say my radius is 5 feet, then my arc length would be 5 times theta feet. If I had a radius of 3 millimeters, then my arc length would be 3 times theta millimeters long, whatever this theta is. So if theta was 2.1 radians, and I had a radius, I have 2.1 that fits around this circle, once, twice, and however many. So 2.1 times whatever my radius is, maybe it's 5, 2.1 times 5. If I have an angle and I have a radius, I can just multiply them together when I'm working in radian measure for the angle, because this radian measure is a number of radius lengths. So if I know my radius length and my number of radius lengths, that tells me those go together pretty well. They're corresponding units. If you had to do this sort of computation in previous math classes and you're working in degrees, there's a whole lot of divide by 360, figure out what portion of a circle it is and something. You don't have to do that if you're working in radians, because radians will come out measuring your arcs in radius lengths. So then just the radius length and the angle are all you need. So I do want to talk about today, this was the main focus of putting all those pieces together and how to see these. This is what we talked about on Tuesday. There's one other piece to this that I want to talk about, because we do have XY axes here. So I want to talk about XY positions around this circle also, and that's what sections 3 and 4 of Module 7 are about, is about tracking motion around the circle, not in terms of just the angles, but in terms of the XY positions within the quadrants and what those patterns have. And this is where trigonometry comes in. Trigonometry, sounds like, okay, we're studying triangles, and yes, there are going to be triangles involved when we're trying to compute XY coordinates in this, because the XY coordinates come from a horizontal and vertical grid. And if I'm trying to figure out where this position is here on a grid, I can say, well, let's say I'm gonna go left by this amount and then up. And guess what happens if I draw lines that go left and up? I've just made a little triangle along the x-axis in that second quadrant. So we're gonna have triangles, and this is related to trigonometry, even though we're not starting from a triangle, but this is the more general form, and then triangle usage, just freestanding triangles, is a specific use of trigonometry, which is maybe more easy to picture because you're always dealing with acute angles. So let's take a look at, let's see, this is what we talked about last class rather. Investigation number 3 from module 7. And there we go. So we're going to look about circular motion. And so we can talk about just positions along a circle, but also circular motion. So suppose I've got this fan here, and this is labeled with 2.6 feet as the length from the center of the fan to the edge of the fan blade, and we've got a fly sitting on the edge of the fan blade, and the fan spinning around. We hope it's not going too fast, or else that fly is getting really dizzy. But regardless of how fast it moves, I can see if this fan is rotating in the direction indicated by that arrow, counterclockwise, just set up so we don't have to do anything tricky to start with. If I want to track where this fly goes, I want to know where it is relative to the center of the fan. I can talk about that in angles and the radius, which is the basis of polar coordinates, which I briefly mentioned. And you might see like module 9 is about polar coordinates. We're not actually going to spend too much time on that, but we will mention it before the end of this semester. It's not officially part of our course, but it's something that's used in Calculus 2 a lot. Polar coordinates are very handy when you're always dealing with angles and circles instead of having to deal with x, y coordinates. Involves a lot less Pythagorean theorem, because we're going to see a lot of that. But using x, y coordinates, I can model where this fly is at all points in time also. So let me just erase this. So I can point out some things quickly up here. Let's pretend that's a circle. So let's say this is the fly's path. So meaning if that fan has a radius of 2.6 feet, let me just use my units in feet on both axes. So this would be the point, for instance, 2.6, 0. It's on the x-axis. The fly is directly 2.6 feet to the right of the center of the fan. But I know it's moving upward. So I'm going to do this in parts. Let's say I just divide that first quadrant into 4 equal pieces. So, you know, like if I drew lines here, I'd have 4 pi pieces of the same size. We could talk about them. Oh, each would be whatever 90 divided by 4 is, degrees, 22.5 degrees. That's not the important part. I just want to talk about, like, visually what's happening. So during the first quarter of this quadrant, the fly's position changes, right? But it's mostly just going straight up. Now, it's not exactly going straight up. This is a circle. It's not a square with vertical sides. But as the fly moves at first, it's almost going just straight up. It's moving in towards the center of the, like if I think about this coordinate point, its x coordinate's going to be a little bit less than 2.6, yeah, because it's moved in a little bit. But this motion that it's had, 1/4 of the amount of arc that it takes to get up to the top of the circle, almost all of the motion right there is vertical in this drawing. You know, the fan's probably on the ceiling, not on a wall, so it's not actually going vertically. But visually in this picture, for that first part, the fly's motion is almost all vertical, or what's going to change is mostly the y-coordinate. And the x-coordinate is hardly changing at all. It's probably still very close to 2.6. So what if I were to, this is down below here, what if I were to track what happens with this fly's position, not around a circle, but if I just track here, and let's start with the vertical changes. So this is like the angle that we've moved through. I'm going to measure it in radians just because, but it doesn't really matter. And I want to talk about its vertical position. So vertical position in this graph for the y-coordinate of the fly. Or how many, in terms of this, how many feet it is above this, what's horizontal in this fan diagram. But if I move upward there, at the beginning, my fly was at a y-coordinate of 0. So when the fan hadn't spun anywhere yet, the fly's y-coordinate, vertical position relative to the center of the fan as it's drawn vertically like this. I mean, maybe it's an exhaust fan, like at the side of a building, so you can maybe see a fan going that way. Yeah, I was doing my fingers the right direction. But let's see. The angle theta that it's traveled through, let's say that this then is the top. So I've divided that into 4 sections. So this is, and you'll see this worksheet refers to as it moves from, from the 3 o'clock position to the 12 o'clock position. I don't want to talk about them as 3 o'clock and 12 o'clock, but let me just put these without numbers. When it's at the top, when it's at the side. Because when we're at the side, we're at position 0 radian, 0 degrees, whatever measurement you want to talk about. We're at the top, you can call it 90 degrees. You can call it 1/4 of 2 pi, meaning 1/2 pi radians at the top. Whatever measurements we're using, just relatively speaking, this is those 4 small, equally pie-sliced sections of the first quadrant there as the fly's motion goes through 1/4 of a rotation. But between the beginning where it starts, the 3 o'clock position, and that first mark, it's going almost all vertically. So as the angle increases to that first mark on the side there, my height increases a lot. I'm just drawing some dot. It's up high. But relatively speaking, even though I don't have any numbers there, whatever this height is, during the next phase, does the height increase the same amount, more or less, during this second portion as compared to the first? So what I mean is, during the first quarter of this quadrant, I went from height 0 to height whatever this is. During the next quarter, so I'm halfway through the first quadrant, go to wherever that is. Now they look about the same size, right? Any guesses as to, thinking about the shape of this circle, are they the same size? Is the second one larger or smaller than the first?
Smaller.
It's going to be a little bit smaller because by the time I'm up here, despite the fact that this is not a very particularly perfectly drawn circle, the circle's curving over. So as it's continuing along this path, it's starting to go a little bit more left-right. This is the same arc length as that arc length, but this arc is more like vertically oriented and this is a little bit tilted. So it's going to move a little bit more left-right and a little bit less up-down. Not a whole lot. It's kind of hard to tell the difference between those two. Now, especially in my circle here, which is not quite circular, but pretty close, you can maybe tell that during the third portion here, it's not going nearly as far vertically. And then during the last portion, oops, let me go up. It's hardly moving vertically at all. So, to kind of translate this into tracking the y-coordinate here, as I rotate, when I went to that first quarter of the way through this quadrant, I went up a lot. During the second, almost as much. During the third, I went up a little bit more, and during the fourth, my y value increased just ever so slightly. So in terms of what happened to my y-coordinate, I'm just going to put in some numbers up here. Like, let's say this is, let me just call it 1 to have a easy number to work with. So I can talk about like, oh, if I say something like 0.5, that's halfway. Now that isn't 0.5, but maybe it's, I don't know, 0.4 or something. And then maybe this height is 0.75, because the distance between those is also pretty big, but not quite as big as that one. And then maybe I'm up to 0.9 by the time I'm at that third spot, and then finally up to 1. So it just went a little bit up. So 40%, 35%, 25%, 10%. Just rough estimates of something. These are those same y values here, but tracking the angle, letting the angle progress as I go here, and then I can keep letting the angle increase. So I don't have to have angles going around in a circle. I'm just tracking these angle measures. So this is at the right side. Like 0 degrees, 0 radians. This is at the top, 90 degrees, 1/2 pi radians. I can go back down to the left side, 180 degrees or pi radians, half a circle. And I could track what happens to the y value. The y value of this fly position would increase and then decrease again. Now this isn't a half circle that I formed. It's a slightly different shape than a half circle, but it's certainly a curve. All right, it's not like a straight line, because we increase a lot, and then slightly less, slightly less, slightly less. And this is going to be symmetric going back down. Now why I say it's not a circle is because I know that circles, when I get to the side, they're very, very vertical. And I'm not going very, very vertical. I'm not going like almost straight up here and then hardly curving over. Because if we actually work out some positions around a circle or use a circle equation, x squared plus y squared equals r squared, 1 squared in this case. So I put it as a 1. We can see that it's not going to match up with these positions here, but how on earth would we ever figure out what those positions actually are? There's a few of them that we could maybe find using geometry facts, like the one smack dab in the middle, because we know some things about 45-degree angles in triangles. If I wanted to know where is this spot in terms of x and y, you learned some geometry facts at some point in time in your past, I'm sure, about 45-degree angles, which is what this would be. And I'm going to make a triangle out of this in terms of trying to figure out what's the x, y coordinates here. I can find the x coordinate and the y coordinate. And by drawing that out like that, you can see I have this 45, 45, 90 triangle, if that rings a bell. Like, oh yeah, it's also isosceles right triangle. It's got many names, but these two sides are the same length, and that's the hypotenuse, and, well, I could say, a squared plus b squared equals c squared, but two of those are the same number. The x coordinate and the y coordinate are actually the same. at that spot. I know, because it's nice and symmetric. And I used 1 there. I'm just going to use 1 for the this is the radius of the circle. It's just at an angle. But these two are actually the same number when I'm at that spot. Just geometry fact. So x squared plus x squared equals 1 squared. 2x squared is 1, or x is going to be the square root of a half, which is not a preferred format. But square root of a half, root 2 over 2, if that sounds familiar. I'm just going to write a square root of a half, because it doesn't really matter the format of it. It's the value of the number that's important. And we'll talk about some like key values that are nice to know off the top of your head, but it's not really the most important thing in life. But we can find some coordinate points like that. If you evaluate this, it comes out to be about 0.7. So 0.7, 0.7. It's 0.707 something something. But if you can maybe see that, what that means is this position relative to the size of the circle, if this is 1 unit out and up, because the radius is 1, I have about 70% of the way to the right and about 70% of the way to the top. No, I had 0.75 written there. It's really about 0.7. There we go. But that's halfway through the quadrant. It's not at the point 1/2, 1/2. Because of Pythagorean theorem and circles and all this, it's actually about 0.7, 0.7 that falls on the circle halfway through the first quadrant. But in any case, these numbers are specific to this having a radius of 1. But if you remember things about similar triangles, if I made it a radius of 2, these would just both be twice as big, twice as far away in both directions. If I made this a radius of 17, I'd have 17 times both of those, etc. But my point is not to think about, oh, well, what are the specific values at these points, but how can we describe these points in general as we go on. This was just tracking the y-coordinates. So, and this is just tracking the y-coordinates through the first 180 degrees or through the first pi radians, through the first half circle of motion. But this pattern of values, this is a specific relationship that's given its own name, so we can talk about it without saying, well, suppose I want to talk about the vertical change of something rotating around a circle and talk about it relative to the, instead of saying all of that, we just say sine. It's the sine function. Like a square root function relates a number to something that is that number multiplied by itself. The sine function relates angles that we travel through to y-coordinates. If we're thinking about motion around a circle, there's other things we can talk about relative to if I draw a triangle inside that circle. But this function here, the y values in this function are the sine values. The sine function is abbreviated SIN. It's not too much of an abbreviation, but the other trig functions have longer names. Of whatever we call the angle. And I called it theta, so y equals sine of theta. So in this graph, the y values in this graph represent what's called the sine value of angle theta, the angle that the fly in this case has traveled through, or that our point in general has traveled through around the circle. So I've got the sine function that represents the vertical position in that diagram up above. If I were to graph out the sine function as opposed to looking at a list of its values by looking at a circle and looking at the positions in the circle, it looks like this to start with, and then it kind of repeats. We'll have some negative values once we pass this left side of the circle, because if we're talking about vertical position relative to the center of the circle or relative to the x-axis, once I've passed that 180 degrees or pi radians, we're going to be down in the third and fourth quadrants where those y values are negative. It's going to have the same sort of patterns of y values, As you can see, if I pass this point here, and I'm going downward, during the first quarter of that quadrant, I'm going mostly down, and then a little bit less down, and so on and so on, until at this last section, I'm going mostly horizontal, but only a little bit more downward vertically. So if I were to continue this, it'd have that kind of symmetry where, oh, it goes up and back down, and then down and back up. It's a very symmetric sort of shape, and if this fly were to spin around over and over, like if it just kept sitting on a fan that's spinning, it would continue to go through this sequence of ups and downs. And this would literally be tracking, in that picture, how far up and down it is as the angle increases. And the angle can increase past one full rotation. It can be 2 rotations, 3 rotations, 4 rotations. But every time it goes through another rotation, visually speaking, it looks just like it did at the beginning. So I could keep drawing this wave shape as the angle increases 2 pi, 4 pi, 6 pi, 8 pi, meaning 1, 2, 3, 4 full rotations. But all of them look just like this first one does in terms of the patterns of y values, or the patterns of positions relative to the center of the fan. And this is just tracking the y values, or the vertical positions in the fan. So the sine function tracks vertical position in terms of motion around a circle. And we use cosine to track horizontal position, which you can see on this one. Oh, well, I start out not at the center. I start out to the right of it, and then I get closer. And then I get to the left, and then I get farther away again. You know, so just starting with the sine function might be like easier because it starts at 0. The y value, when we start at this initial position, is 0, and then it increases and then decreases. So you can start at the origin and then decrease back till we get to this equivalent over here. So what I'd like you to try to do, this part F asks you to track the horizontal distance, which is what the cosine function is for. But what we did with this vertical position, as we went through that first quadrant, take a couple minutes and see if you can sketch out an equivalent sort of graph for what's going on with the horizontal position relative to the center. So meaning, and I just said suppose it's a radius of 1. I think the original fan question said it's the radius of 2.6. It doesn't really matter whether it's 1 or 2. The shape is going to be essentially the same. It's just, what is this y coordinate? Is it 1 at the top, or 2.6 at the top, or what is it at the top? We're still the same portions away, the same proportion of that. But think about, instead of those vertical components, what if we were talking about the horizontals, or when I start here and travel to this first stop along the way, how has my horizontal distance changed? So my vertical position, I drew these lines and like, oh, it's different horizontal amounts. But here I am at 2.6. Here I am at almost 2.6. Here I am at, well, a little bit less. And then finally I'm starting to move horizontally during those last couple of sections. So tracking what the x coordinates are as I move through that first quadrant counterclockwise, which means the x coordinates are shrinking. You can see even as I just try to draw this, we end up with a bunch of triangles. It's a little bit messier to draw, or more challenging, I think, to draw the x-coordinates, even though it's the same sorts of numbers, same sorts of values and patterns, just starting in a weird spot of the graph. The other weird part about this is, if you label this, your, your y-coordinate here in this graph is tracking the x-coordinate in that fan rotation, so that I think is the other part that's a little bit more challenging about this. But if I want to track this horizontal location here, and like I said, the original fan said, oh, it's radius of 2.6, but let's just say for simplicity's sake that this is 1. To be able to talk about percentages easily. So when I'm at the beginning, when I've not traveled through any angles yet, when I'm at angle 0, 0 degrees, 0 radians, 0 whatevers, I'm 2.6 units to the right, or positive 2.6 in the horizontal direction from this. So at angle 0, or not 2.6, we're using 1. I'm 1 unit to the right, or I'm all the way to the right. So all the way to the right is 1, or 100% of the way to the right. And as this angle increases, my distance to the right decreased a tiny bit during the first quadrant, or the first quarter of this quadrant. 1, 2, 3, 4. So between angle 0 and angle a quarter of the way, so whether 22.5 degrees or pi over 8, very small number of radians, a quarter of the way through the first quadrant, this distance to the right is decreasing just a little tiny bit. If this is at 1 here, then this is at maybe like 0.9, left to right. So 0.9 comma something. Whereas this is at 1 comma something, well, it's 1 comma 0. Or tracking the x-coordinate. So by the time I'm here, I've gone down, but hardly at all. I'm still at 90% of where I was before, if I'm saying that's about 0.9. So if it was 2.6 overall, and now I'm at 90% of 2.6, but I don't want to figure out what that is. By the time I'm at this center of the quadrant, now we did just figure out where that spot is. It's like 0.7. At pi over 4, 45 degrees. We're a little bit more to the left. 0.7 comma something. But that's a decrease of 1/10 in the first first quarter circle and 2/10 in the next quarter circle. So we're decreasing more rapidly, like going downhill faster. Even though this looks kind of like a straight line the way I have it drawn, it's not actually a straight line. It's easier to see in the next quadrant because by the time we're to 3/4 of the way through, we're going a lot to the left. This looks like, maybe it's about, what, 3/4 of the way through or something? So maybe this is about like 0.3 or something, comma something. Just eyeballing it. But it's dropping quite a bit. Actually, I shouldn't drop that much, maybe it's 0.4. Because I want to be able to decrease it most during that last interval. So this is spread out a bit. But the x-coordinate's decreasing as we go through that first quadrant from 1 down to 0, but it's not in a straight line. It's decreasing less at first and more later on. And then if we're to continue past that 90-degree mark, past the top of the fan, the x value would continue decreasing. It turns into negative values. So instead of being to the right of the center, I'm to the left of the center. Or if I'm tracking my x-coordinate is now negative for the next half a circle, or quarter of a circle rather, half pi. And it's going to go through the same sorts of values, but kind of with the reverse pattern. As I go through, at first I'm going mostly horizontally. So my value changes from x value of 0 to x value of, well, it should be kind of similar to that one, right? Whatever we said that was. That was 0.3 or so. So this is at negative 0.3. Comma, as the, well, it's the y coordinate in this. Negative 0.3 in the circle is the x coordinate. As I continue to track the x coordinate, maybe it's about negative 0.7. And then negative point, who knows, 9, before it finally gets to negative 1. But it's going downward, but going downward first quickly and then more and more slowly as we go on. I apologize, these numbers don't quite match up, but you generally kind of get the idea. Maybe this should, oh, I said that should be maybe 0.4, right? I think I changed it, yeah, I changed it up there, but not over here. But in any case, we have this pattern that goes like this. Now if I were to continue around the circle, tracking x values, my x value is the most positive here, the most negative there. And that's what we've done so far, gone from the most positive to the most negative. And if we continue, the x value is going to get closer and closer to 0 again. So that would be O. And then this goes back up, gets closer to 0 again, falling through the same sets of values. And then it's going to become positive and go back to positive, as positive we can be, which was 1 or 2.6 relative to a fan, whatever we have. But the idea here is that whatever size your circle is, if we're tracking circular motion, we're going to have these same patterns. It's just a matter of like how big is your circle depends on what's the precise x and y values. When I wrote out this, we were talking about the y coordinate, and I was using 1, so like 0.4, 0.7, 0.9, and 1 up at the top. If I have a circle that's not 1 unit in diameter, but 2 units in diameter, well, the y value is twice as big. Or if the radius is 17, the y value is going to be 17 times as big. But it's just all scaled up. We've got similar triangles or just larger circles. All the angles and relationships are going to be the same inside, just the distances get scaled up. And so it's the difference between looking at it on your screen and looking at it on this board here. It's the same relationships. By projecting it, I didn't suddenly change all the angles. It's just bigger. All the distances that are measured get larger. And since this is measuring distances as the output of this, the input is an angle and the output is a distance. Scaling that up is important So there's one other piece to this that makes it useful, like in general, as opposed to just applying to this one circle with a radius of 1. But a circle with a radius of 1 is kind of useful as a reference point, if you can just remember to scale up afterward. Bring this down here. So more in general, if I want to talk about a circle with a radius of r units, like we did at the beginning when we were talking about arc length, and angles of theta, regardless of where they are, just kind of draw it in the second quadrant for fun, but it doesn't matter what quadrant this angle's terminal ray is in. I can talk about the arc length, which is that length there, as being just the radius length times the number of radians. If I want to talk about this coordinate point as an xy point, the y value is tracked by the sine function. So I can find the y value by using the sine of this angle. I just have to scale it up to a circle of radius r. So it's r times the sine of the angle. The function that tracks the x-coordinate around the circle is the cosine function, which is abbreviated COS. Oops, and I just wrote it. But again, that gets scaled up if I'm talking about a circle with a radius of more than just 1. If I'm talking about radius lengths versus just actual number of units, I need to use the radius length times the cosine of theta. So this cosine function relates an angle and an x-coordinate. This r is going to be fixed for any one thing. If I'm thinking about motion around a circle, r isn't changing. This isn't a variable. It's like just some sort of number. It's like the m and y equals mx plus b. It's just some number there. We'll use a symbol for it for now. But it's representing some fixed quantity. Because if you're changing circle sizes, that's kind of a weird instance of a problem. But if I'm talking about circular motion, I have a fixed circle, or this is some specific value. As the angle changes, the x value is going to change. So input x, or input theta and output x. Or for the sine function, input theta and output y. Again, for some fixed value of r, for any specific circle value that you're talking about, or in terms of triangles, which we'll get to later, this radius turns out to be the hypotenuse of any of these right triangles. So it's related to, like if you're like SOHCAHTOA sort of stuff, it's still related to that. But it's just we don't have to have a whole triangle drawn out. We can just talk about xy points and angles without needing to compute, but there always are triangles that can be drawn in to measure these distances. It's just that, like for instance, in this position here, the x value is negative. We don't usually have negative numbers listed as lengths of sides of triangles, but we could draw a triangle and the absolute value of this x would be the length of the horizontal side of the triangle, whether I draw it down here or up there, just measuring between the vertical axis and that position. That's how we measure our x values. How far am I left to right in this? How far am I from the center? So in any case, our general patterns for these are 3 relationships that are good to know. If I'm dealing with a radius of 1 unit, or if I'm just talking about these quantities in radius lengths, in terms of radius lengths, the arc and the angle in radians are the same. The sine value and the y value are the same. The cosine value and the x value are the same in radius lengths. Or if my radius is 1, those would have the same number of units on them. So if I have a sine of something equals 7, that means the y value is 7, but that can't happen because I can't have a sine value, like what percent of the way am I? Oh, 7. It's not 7%, that'd be 700% of the way to something. So you can see that these values, just like when we were tracking this around, I used 1 as the top. That's like 100% of the way to the largest value I can have. These sine values and cosine values on their own, these are always going to have values between 1 and -1. I can be up to 1 radius length to the left or right, -1 to 1 of the center. I can be within 1 radius length above or below, +1 or -1 radius length from the center. I can't be more than, if I'm on a circle, I can't be more than 1 radius length away from the center in any direction. That's the maximum. So these functions both have a range that's -1 through 1. -1 through 1 with brackets, because they will have values of, will have values of exactly 1 and -1 when they're at their extreme points. The sine value would have a value of +1 here and -1 there. Cosine would have +1 here and -1 there, because they're related to, sine is about the y values, and x is about, or cosine is about the x values. If, like, you can memorize that just as a fact. The way I always remembered it when I was learning about these is like sine and y, they kind of sound the same like vowel sounds in them. And, well, x is a cross. X, it's a cross, and x is a cross. But cosine is a cross, so x and cosine, that's harder to remember. If I had sine and y, those kind of sound the same in your head if you say them. They've got that same vowel sound, so if you're like getting confused about what's what, and it takes something to remember which one goes with what, sine and y, and then cosine's a cross. They both go that sound in them. But in any case, that's just a mnemonic thing. But if you can picture them, just remember they're both tracking the coordinates for circular motion when we're talking about using them within a circle. We will talk about tangent functions also, and also some reciprocal functions, but those are less about circular motion and just about relationships between measurements. So, is there anything else in this 7.3 I wanted to talk about? I don't think so. So let me go on to this so this is investigation 7.4. And so we're, instead of having a fly on a fan blade, now we've got a skiing trail. And the radius of this skiing trail is 1 kilometer. And so if I've traveled around this circular trail an angle that's 1 radian in size, that means I've traveled 1 kilometer so far. Or it's about 6.28 kilometers all the way around this trail once. So I'm going to move this up a little bit, but if you have this circle here, it asks, what's the angle measure in radians at the angles of the angles that have an initial ray passing through 0, 0, and 1, 0. So the one that's drawn starting from the center of the circle out to the right, with the terminal ray going through 0, 0, and these other 3 points. And so just labeling those in radians, or think about what those measurements are in radians. And then for those that aren't 0, if you can come up with what the decimal form is approximately for them, instead of having multiples of pi, which some of them do. Remember, pi is not a unit. It's very easy to think of it as a unit, and if you seeing it tagged on to the end of numbers, pi is 3 point something. so angles, if I have these coordinate points out there, if I have an angle that's just like, I haven't gone anywhere yet, initial and terminal ray are both here, that's 0 radians, 0 degrees, 0 whatever I'm gonna measure in. If I'm in radians, in exact form, what's the measure that's equivalent to this, like 90 degrees? What's the measure in radians of that angle? Yeah, pi over 2, or 1/2 pi, right? 2 pi radians is all the way around. 2 pi radius lengths takes you all the way around a circle, 2 pi r. So a quarter of the way around is 2 pi divided by 4, otherwise known as pi over 2. Or you can write it as 1/2 pi, as the number of radians is the angle that rotating through that would put us at this spot. All right, so before we go into the other ones, I want to point out, again, this is a circle with radius 1. Our ski village has a track with a 1 kilometer radius. So if I wanted to measure this arc length here, I need to know theta and r, which is, let's see, theta, and r is 1. So the distance I've traveled is pi over 2 kilometers, or 1/2 pi kilometers. True, but kind of weird. If you want to say that in maybe a way that somebody would understand it, how far did you ski? Pi over 2 kilometers. That's kind of weird. Maybe say about 1.5 kilometers. That sounds normal. So like if you divide this out, pi divided by 2, it's what, 1.57-ish?
Yeah.
So it's about 1.57 radians also. But using our arc length, s equals r theta, if you want to talk about how far you skied to get there, radius length times theta, 1 kilometer times 1.57 radians gives you 1.57 kilometers traveled along the radius. So this arc length is 1.57 kilometers, approximately. Between point A and point B. But since we know the xy coordinates, we also know some facts about sine and cosine at this point. X and y, the xy position around a circle, are related to the radius and the sine of theta, cosine of theta. So, well, look, my y value is 1 right here. 1 is r sine of theta. Well, my r is 1, so 1 equals sine of theta. Oh, and theta's pi over 2. If I were to write out that y equals r sine of theta and fill in the numbers that I have 1 equals 1 times sine of pi over 2, or sine of 1.57. Or in other words, here's a fact. Sine of pi over 2 has a value of 1. If you have a calculator in radian mode and you put sine of pi over 2, it'll give you 1 as a result. That's the relationship that goes with that. Similarly, cosine of pi over 2 is equal to 0. We can get that. We have a radius of 1. The cosine relationship has an x, not a y. But x is 0, radius is 1, and the angle that we're talking about is pi over 2. Cosine of pi over 2 is 0. Or in other words, based on knowing this coordinate point, I know, without grabbing a calculator, the sine and cosine of 1/2 pi, or the sine and cosine of pi over 2, or 1.57 radians. The sine is the y value, and the cosine is the 0 value, the x value. using that same thought process without redoing this whole thing, since we've still got a radius of 1 every time, I can see that those equations are always going to just reduce to, oh, y is sine theta and x is cosine theta. So if I know what this angle is here in radians, I also know its cosine and its sine value. 180 degrees, but in radians, that's also known as, oh, halfway around a circle is how many radians? Pi, right? So at this point, I'm at pi radians. So I can identify points by knowing what circle they're on and their angle. I can also identify them by xy points. It takes a couple of numbers. You can't just locate a point in two-dimensional space with a single number. It takes two numbers. But radius of 1 at pi radians angle, or xy -1, 0. But that means that the cosine of pi is the x value there. And the sine of pi is the y value there. So we also were tracking, this is a picture of our cosine value. We didn't quite get to pi. Pi would have been the spot here where we've gone through one quadrant, through two quadrants, we're back up over there. Actually, down to here. Through one quadrant, through two quadrants. Sorry, I was thinking of my sine curve all of a sudden. But at that point, when the x-coordinate is -1, this is our cosine curve. This means we're halfway around the circle. So this is pi. That's pi over 2 radians in terms of the angle we've traveled through. Or you can call them 90 degrees and 180 degrees. It doesn't really matter. It's just more succinct. But in any case, these xy coordinates, when we're on a circle of radius 1, the xy coordinates exactly match up with the sine and cosine, because the r part of that just turns into a 1 multiplied on. We can scale it up. If I suddenly had a 6-kilometer radius, these points would be like 6, 0, 0, 6, -6, 0, and so forth. But the sine and cosine values are still the same as what they are before. The x and y coordinates would be larger at those points, and the radius would be larger. They cancel one another out. The sine and cosine values still come out to be the same things if we're thinking about solving for them. The sine and cosine values don't turn into like 6s and -6s. But in any case then, I can think about these quadrant angles. 90 degrees or pi over 2, 180 degrees or pi radians, or about 3.14 radians. Meaning, if you've traveled this far, you've traveled about 3.14 kilometers around the circle, around the ski path. And at that time, I've got sine and cosine values at pi over 2. I've got sine and cosine values at pi. What angle is it that would take me 3/4 of the way around the circle? How much?
In radians?
Yeah, in radians. 3 pi over 2. You can also call it 1.5 pi or 3/2 times pi. However you want to write that. I'm going to write 3 pi over 2. That would put us, if that's our angle of rotation, 3/4 of the way around, which maybe it's easier to see if you write 3/2 or 1.5 pi, because 2 pi is all the way around, so 1.5, oh, that's 3/4 of 2. However it makes more sense to you, you can write it either way. But that's the angle in radians that takes us to here. Cosine, sine. Cosine of 3 pi over 2 is 0. The sine of 3 pi over 2 is -1. Or, oh, I erased the sine graph that was previously here to show that, but this is the 3/4 of the way back to where we started graph. So we're like at this point on the sine curve. We increased vertically and then decreased back to a y value of 0. And then we're at our lowest point 3/4 of the way around before we go back to where we started. In this graph, that would be before we go back to where we started. So 0 and 2 pi and 4 pi and 6 pi and 8 pi all have the exact same cosine and sine values, 1 and 0 respectively, because they all appear as angles drawn like as a circle, a central angle of those measures. They all are coexisting angles, so the same angle. They're called coterminal. They look like the same thing regardless of how you got there. Their sine and cosine values, which just track location relative to the center, not distance traveled along the arc, are all going to be the same value when we're in the same position relative to the circle. So cosine of 0 or 2 pi or any multiple of that is going to be 1. Sine value of any of those, 0, 2 pi, 4 pi, 6 pi, are all going to be 0. So again, the y's and x's correspond to sines, sines and cosines respectively. Like, what order did I just say those in? When we have a radius of 1, if I scale up the circles, the distances change, the y values and the x values change, but so does the radius. So both halves of those equations get multiplied by the same factor. If I increase the radius by a factor of 5, the y and x values are all bigger by a factor of 5 also. The sine values and cosine values don't change. Those are just the relative positions to the center of the circle. Left, right for cosine and up, down for sine. All right, so let's see. Don't really want to go through these computations. Is this the one I was looking at? No. There we go. All right, so let's take a look at this. This is question number 4 here. It's a second Arctic village. So we've got, here's our Arctic village with a ski trail that is also a circle, this time 2.5 kilometers. So this is starting at a harder question. This is what we're going to talk about a little bit more on Tuesday next week. But in this case, we have an arc measurement that's given, 2.75 kilometers as a distance traveled around the path. But we've got 2.5 as the radius of this circle. The first question asks is, explain what, and that's really small up here if you can't see that, 2.75 over 2.5 represents in this context. So just think about, we started skiing from this position 2.5 comma 0 and ski counterclockwise for 2.75 kilometers before stopping for a rest. So think about what on earth 2.75 over 2.5 would represent. Hold on for just a minute. And then we're going to think about some ordered pairs. But yeah, you had an idea?
Yeah, will you give us a theta?
Yes, exactly. That's an arc length and a radius. And if I divide an arc length and a radius, I'm going to get something slightly more than 1 in this case. We say, oh yeah, the arc length's slightly more than the radius. It's slightly more than 1 radius length. Slightly more than 1 radius length means I've got an angle that's slightly more than 1 radian. It's our angle measure. That top relationship over here, S equals R times theta. If I know S and R, the radius length and the arc length, when I've divided them, S divided by R, I've got theta. I've got theta measured in radians. And it might not be natural to jump to an equation, but if you see, well, why would it be dividing an arc length and a radius? Maybe you think, like, what sort of number do I get? It's just a little bit more than 1. Thinking about that, it's like, oh, it's a little bit more than 1 radius is how far I've traveled along the edge of the circle. So it's a little bit more than 1 radian is the angle that it makes. If I were to draw from the center up to that point on the edge of the circle. So let me erase some of this, but look at this second question. It says determine the ordered pair in radius lengths that identifies the exact location where the skier rested at this spot, 2.75 kilometers in. Now, how on earth are we going to find coordinate points just from that? XY coordinate relations. So this is where we're going on Thursday, but yeah, have an idea?
Yeah, so first we have to find theta, which means we divide the arc length by the radius.
Okay.
And then if we want the x coordinate, we use cosine, which means cosine of theta
Mhm.
times the radius of the same theta.
Exactly. Good. So again, we can divide this out and get 1 point something, or if you want to leave it in exact form, you can just write it like that. I'm just going to use the symbol theta, but we know a numerical value for it. It's 1 point something. But yeah, if I want to find x and y, all I need is to write out those expressions up there. X is the radius times the cosine of theta, which theta is this. I'm just writing theta for brevity's sake. And the y value is the radius times the sine of theta. So if I grab a calculator and put it in radian mode, which graphing calculators are usually in radian mode by default, unless you put it into degree mode for some previous class, it's going to be in radian mode. If you type in 2.5 cosine of this, you're going to get some sort of decimal value. That would indicate that x value here, it should be something between 0 and 2.5. Or in other words, it's going to be 2.5 times something that's a little bit less than 1. And this is going to be 2.5 times, again, something that's a little bit less than 1. So if you can see these three relationships up at the top, using them in combination helps us take the information that we're given and answer these sorts of questions. From a radius and an arc length, I was able to determine an angle. And using that angle and the radius, I can write expressions for or evaluate with a calculator, not things to do by hand. Decimal values for the XY positions along a circle. So these all play together. Keep those three in mind. I think they're very handy to just have written down while you're trying to remember them, or just whenever you're working on things related to circles and angles and lengths. Those are going to save you a lot of time. You usually have enough information to solve for a missing piece, or to be able to express a missing piece more succinctly by solving one of those equations up there. Because S and R and theta and X and Y are all different pieces we might need. S and arc length, theta and angle, R, the radius, X and Y refer to XY positions around a circle that we're traveling on that has radius R. So as long as you can imagine what these pieces are, know what you're thinking of, but also remember what radians mean. A radian measure for an angle is a number of radius lengths traveled around a circle or placed on a circle if we have an angle drawn into standard position. But in any case, that's it for today. I will post some additional stuff moving forward for sections 5 and 6 of chapter 7, but between now and, let's see, tonight you have 7.3 and 7.4 lessons to do. That's related to the stuff we talked about today. By Tuesday night next week, you have the homework for those same two sections for the stuff that we talked about today that's due. It's a lot of this circles and tracking motion and using sine and cosine functions. Not a lot of computation things, but you'll see a few like doing things like that. You can write them in exact form. Remember, when you're entering things into iMath, you don't have to compute it out in advance. You can write an expression just like that. What's theta? It's 2.75 over 2.5. Or what's the x value? It's this, but write in that number there. So that said, also 2 weeks from today, the gateway exam is due, or gateway assignment is due. It's not an exam. That is a bunch of algebra technical practice, like practice at solving equations with square roots and practice at getting common denominators with x's involved and stuff like that. It's kind of just tedious sorts of careful attention to detail algebra work. not major concepts involved, it's not story problems, it's just some like simplify this, square this, factor this, some things that I want you to remember, and make sure that you're still good on going into calculus, but it's not major focus of the class. That assignment you can do as many times as you want. It just counts as a homework assignment, although it is like 50 questions, so it's a, relatively speaking, it's kind of long, but start working on it. You can do all the questions as many times as you want for full credit on that one. All right, so that's it. Oh, other thing I wanted to mention, withdrawal deadline. You all are here attending regularly, but the withdrawal deadline for class withdrawal is this upcoming Sunday. That's what that WDD is. Tuesday.